Okay, this is going to be our fifth video on electromagnetic induction. Um, Let me start with a little bit of an apology. In the last video, I said that we would only have one more video on this topic, um, and it's true that there's only one more section that I want to cover, which is 29.7, but this is a pretty long section, and rather than make a super long, like 90-minute video here, I decided to break it up into two separate, shorter videos. So instead of one more video, you guys are going to have two more videos here. So it's basically this video and then one more after this. Okay. So in this video, we're going to be covering the first part of section 29.7, and section 29.7 covers displacement currents and Maxwell's equations. So in this first video, we're going to talk about displacement current, and in the second video, I will do Maxwell's equations. Okay. And so we'll get right into it here. I am going to be pausing the video a couple times because I've been having some technical difficulties and I lost a previous recording of this video, so I'm doing this one again. But let's hope it's not too much of an interruption to the actual lesson here. Okay. So in the last video we saw how varying a magnetic field can give rise to an induced electric field, right? It also turns out that varying an electric field is going to give rise to a magnetic field. Okay, and this is a really important sort of symmetry of nature. Without this fact that changing magnetic fields induce electric fields and changing electric fields produce magnetic fields, we wouldn't have electromagnetic radiation. And electromagnetic radiation really covers everything in the spectrum, from radio waves to visible light all the way out to gamma rays. So really, this is sort of one of the very important sort of symmetries that really allows our universe to look the way that it does. Okay, and so without getting too far into this, we're going to talk a little bit more about sort of bringing together some of these ideas when we talk about Maxwell's equations, and then more about electromagnetic waves and electromagnetic radiation in a couple of chapters if we have time to get there. But before I get caught up with all that, let's focus in on the topic at hand right now, which is displacement current. Okay, so we haven't introduced displacement current yet, and to get there, we're going to take a look at Ampere's law. And in looking at Ampere's law, we're gonna first realize that Ampere's law can be broken, or at least the way it's written now, in the way that we understand current to be, Ampere's law is somewhat incomplete. Okay, and so in fixing Ampere's law, in generating a more general version of Ampere's law, we're going to introduce what is known as the displacement current. Okay. And let me before I get into this, let me start by pausing and seeing if this is actually working. Okay, so let's get into it here. So we have Ampere's law. I've rewritten it here, and we know that what Ampere's law is telling us is that this integral around the closed loop, this Amperian loop of B dot dl, is going to be equal to mu naught, our magnetic constant as we call it here, times the current enclosed, right? We're now going to relabel current. So generally speaking, we use current, well, we use capital I to mean current, right? But what we're going to do now is we're going to take the current that we normally use and we're going to write it down as a lowercase sub c. This is going to mean, well, at least it's meant to mean that we're talking about a conduction current. So all the currents that we've talked about up to this point have always been conduction currents. Conduction current meaning just a current running down a wire, the same stuff we've been talking about, right? So when we look at this setup, and this is the setup that's going to sort of demonstrate the breaking of Ampere's law. But when we look at this setup, we see IC coming along this wire, and it's moving positive charge onto our capacitor plate, and we have another IC bringing positive charge off the other capacitor plate, and what we're looking at here is the charging of a capacitor, right? So IC here is what we would normally think of as capital I, but now we make this distinction. It's called the conduction current. Okay, we use IC here, and your textbook uses it too, just to distinguish it from a different type of current, which is going to be displacement current, which we're going to introduce sort of now, right? So we need to be able to distinguish between our regular run-of-the-mill current that we see all the time and displacement current, which we're going to be talking about in a second here. Also, I want to note that the textbook makes sort of a big deal about using these lowercase letters for sort of I's and V's and Q's and a few other things in different places, where they want it to denote the instantaneous value of some quantity. I don't think it's a huge deal, but they do it, so I will use it also so that we're consistent with the textbook. And if you guys want to be able to look through the textbook and follow it, it'll have the same notation that we use. Okay, so lowercase i's here are still currents. I would normally write them as capital I's. They write them as lowercase i's in this case because they're kind of meant to be values which are constantly changing and aren't really going to be able to hit a sort of steady state, sort of. Maybe don't read too much into that. Just think of them as the usual I's and V's. So these are our currents and our potential differences, and we're going to see lowercase q's, which are going to be our charges and so forth. Okay. So now, like I said, we're going to be looking at a situation here where we're breaking Ampere's law. Okay. So let's start off with a situation where we don't break Ampere's law. Let's take a look at this setup of our capacitor charging. Let's say we wanted to find the magnetic field at some point A here. Okay. To do that, we would set up this Amperian path. We have this path for Ampere's law, which we would sometimes call an Amperian path. We would set that up. We would want to use Ampere's law, so we would want to use B dot dl is equal to mu naught I enclosed, right? And if we did this calculation and we used the open surface, which is bound by our closed loop here, the open surface, which is basically just this disk here, and we looked at the I enclosed in this that passes through this disk. Basically, this is what I enclosed means. Well, we would end up with IC, right? So our I enclosed using this open surface here is IC. So that's great. We could do the calculation. We know that the integral around the loop is pretty simple to do for a circle. This would simplify down. We would end up with a B2 pi r, and we would have mu naught IC on this side. We could solve for B then, and that's great. Our B would be non-zero, and we could easily solve for it. Now, we often choose these sort of plane-like or disc-like surfaces to sort of seal up our Amperian loops, right? So we have an Amperian loop, but really we're not required to choose a simple surface, a simple open surface over which we want to do our integration. I could choose a surface that looks like this, let's say. So again, this is my Amperian loop, the green that I'm drawing here. But I could choose a surface, an open surface that looks like this, let's say. Let's say I want to choose an open surface that look like that. So it kind of looks like a bag, right? You can imagine this is my surface. It's like a large bag. You could put your hand in through the red area here, which is now an open surface, and all this stuff is just like a closed surface. Well, an open surface with just this opening, and the rest is all sealed off here, right? So if you chose that surface to do your to be the surface through which you're finding your enclosed current, well, you'd still be okay, right? You could still do the integral over the loop, right? It doesn't change the loop. You're still doing the integral around this loop here. So the integral is still easy, no problem. And if you're looking for what current is sort of enclosed, well, what punctures through your bag here? Well, IC punctures through the bag out this side, and so the whole thing works again. You do the calculation, you end up with the same result for the magnetic field at A here. Let me now get rid of this green bag thing here. Okay, and so after having gotten rid of it here, we're going to look at a third possibility here. Let's say that instead of choosing the big bag that I drew there before, or the disc that we had originally, what if I choose this bowl shape, this bulging surface that they have labeled on their diagram here? If we choose that shape, we run into a bit of a problem. We can still easily do the integral around our Amperian loop, right? Still a circle, still easy, except what is the current enclosed? Well, the current enclosed has to be whatever is puncturing through whatever that open surface is. And in this case, there is no current puncturing through the open surface, at least no current in the way that we would normally describe it, right? There is no IC running through the surface here, right? And so the right-hand side of this is going to end up being 0, which means our B has to end up being 0. But we just saw that B is not 0. We just calculated a B a couple of different ways that gave us the same result, and our B was non-zero. Excuse me. And so this is a contradiction, right? We run into an issue here, and this kind of breaks the most simple formulation of Ampere's law. What we need here is some sort of a new concept to rescue Ampere's law, and in finding this new concept, it's going to kind of open our eyes to this idea of displacement current. Okay, so let's go down here and follow the conversation from the beginning of this paragraph over here. So what we want to do is we want to take a closer look at this bulging surface, right? The surface that we're looking at here, this bowl-shaped thing, and note that, okay, so there is no IC passing through it. We have no conduction current going through the bowl. But what we do have going through the bowl is an electric field that's changing in time, right? And that means that we have electric flux that's changing in time, right? We have an electric field set up here. It definitely goes through the bowl. It's uniform between our plates, and so there's an electric flux which is passing through, which is changing over time as this thing charges up, and which is passing through the bottom of our bowl. And so we're kind of left to wonder, well, maybe this electric field or this changing electric field can kind of lead us to some sort of an idea that's going to help us rescue Ampere's law and give us the answers that we know we need to find, right? So the first thing that we might want to do is write down we're trying to explore what this electric field is going to kind of do for us, right? And in doing that, let's just start writing down a number of things that we know about the capacitor, about the electric field, about anything that might be happening in that area, right? So if we wanted to, we could start out by writing down the instantaneous charge of the capacitor, which is going to be equal to Q, which is Q equal to CV. And again, here we're using these lower cases because Q is our instantaneous charge on the capacitor, and V is our instantaneous potential difference across the capacitor, right? But we know we can also write the capacitance of our capacitor, C, in these terms here from work we did earlier. So we could write it as epsilon naught times A divided by D, where A is the area of this plate and D is the distance between the two plates. Okay, so we could write it out like that. We could also write the potential difference across the plates in these terms, right? And we can kind of see that right away if you guys think back to the sort of term test that we did. You can kind of think back and remember that you can write the electric field in terms of volts per meter, right? Well, if we just rearrange this, we can always write our voltage as the electric field times some distance, right? And so that's exactly what we're doing here. And if we take all these expressions, these three expressions, and we use the fact that the electric field is uniform between our parallel plate conductor, which it very nearly is, right? And then we finally use the fact that we can rewrite that we can write EA, the magnitude of our electric field times the area of our capacitor plate as as our electric flux. Well, then we can come up with an interesting expression here. So let's start off. We start off just writing out the charge on our capacitor in terms of C and V here. We can then substitute in for C and V with the expressions that we have here. If we do that, we get this expression. Clean it up, we end up with epsilon naught times the magnitude of our electric field times the area of our capacitor plate, and replace the EA here with the electric flux. and then we end up with this expression here. So basically we have Q is equal to epsilon naught times our electric flux. But we know that the time derivative of Q has to be equal to our IC, right? Our IC is what's bringing, it's what we think of as our normal current, and it's bringing in these charges, right? So the amount of Q that we have on the capacitor plate, sort of by definition, is the current that's bringing that current in there, right? Or the current that's bringing that charge in there. And so we can simply take the time derivative of our Q here, and if we do that, we can rewrite it as IC, which I've done here. And then if we take the time derivative of this side, well, our permittivity of free space, or our electric constant, or however you want to call it, isn't changing in time. So the derivative only bites on to our electric flux here, and so we end up with this expression here. Okay? And so that's fine. That's great that we have that expression, but we haven't really made a big leap here. We've just written down our current in terms of some other variables in the problem, right? But this is where we need to kind of make a bit of a leap. Okay, so we're writing our current in terms of these variables over here, but maybe we can actually interpret this right-hand side of the equation as a current itself, right? So let's do that. Let's call all this stuff over here this epsilon naught times the time derivative of our electric flux through that open surface. Let's call this our displacement current. Okay, and then in this problem for a parallel plate capacitor where we just have the one wire and just the one IC, well, in this case our IC is going to be equal to ID, and our ID is defined as this collection of variables. Okay, so we've defined this new displacement current, and if we now take this displacement current and add it back into Ampere's law in the way that we see down here, we get this more general form of Ampere's law. Now really, everything that we see here is still just I enclosed, but we've broken up I enclosed into what we normally think of as current, our conduction current, the current running down the wire, but it now also includes this displacement current, this current that we can sort of think of as the electric flux changing in time, right? And so now we have two different potential ways to get a current when we're looking at current going through our open surface. Using this new version, this new more general version of Ampere's law, we can revisit this problem from above. Okay, and if we do, we're going to find that we no longer have this contradiction, right? If we look at this bulging surface, we know that the left-hand side works out fine. We end up with our B times 2 pi r. On the right-hand side, we have our mu naught, and before we ended up with a 0 when we did this bulging surface, right? We did the disk here, and it worked out fine. It gave us an I enclosed of IC, and if we did the big bag that I drew, we ended up with an I enclosed of IC. But when we use this bulging surface here, we didn't. We ended up with no I enclosed, right? But now there is electric flux that's changing in time, going through the bottom of our bowl, or whatever you want to call it here, right? And because of that, I enclosed, which we now know can be IC plus ID enclosed, well, we're still going to have 0 for IC enclosed, but our ID is non-zero, okay? And if you do the calculation, and you use this value, and you actually pull out the electric flux, and you do the calculation, and you realize that ID is equal to IC, well, you're going to end up with exactly the answer that you would have ended up had you used this disk as your open surface, right? And so that's great. We've kind of rescued Ampere's law, and in the process, we've built up this idea of a displacement current, which can be used here and in other places. Okay. So just like our regular conduction current has this idea of current density, well, displacement current has a corresponding idea of displacement current density, right? And so we can write our current density, our displacement current density in this way, just like we could write our regular current density. We can also write our displacement current density like this, and this is actually going to be Pretty useful equation, so I'll box that one off. And so we should just keep in mind that we do have this concept of current density. We're going to use this idea in an example that I have set up down below. Okay, so before I move on to the example, let's just quickly note that so we've built this idea of displacement current to help us rescue Ampere's law. But in addition to that, it kind of gives us a more generalized idea of what a current can be. So now we have this idea of a current that can flow through a capacitor, and it's going to give us a way to write a more general, or at least to understand Kirchhoff's junction rule in a more general sense, right? So if we go back, and I'm not sure we'll have time to, but if we do, we can go back and take a look at some problems using Kirchhoff's junction rule now with this understanding of our displacement current, and see how this changes the way that we can handle some of those problems. Don't worry, obviously, if we have time to look at it, we'll look at it and gain an understanding of it. If we don't have time to look at it, I'm not going to ask you to use a displacement current in a problem with Kirchhoff's rules when we haven't looked at it, right? So if we look at it, we look at it. If not, then we'll just have to skip on it for now, okay? Okay, so the textbook goes on to talk about a couple of, well, let me pull it up here. What does the textbook do? Okay, yeah, so the textbook goes on to talk about the reality of displacement current. So they sort of try and enter into this discussion about whether or not displacement current is actually a current that's sort of real. And then they go through this calculation of the magnetic field, but they don't do it like an example. They just kind of put down some results and kind of state that, yeah, there is a magnetic field inside well, between the plates of this capacitor, and so clearly there must be something like a current in there inducing this magnetic field. So I think that's a good argument and an interesting point to make, but I think that we can also do an example with this. We can actually calculate this magnetic field, which is what I'm going to do, and I think it might be more instructive than just sort of going through a sort of argument as to whether or not this displacement current is a current that we should actually think of as being a real current. Okay, so that's what we're going to do here. I am going to, well, let's say here I'll sort of write out a problem. Let's find the magnitude of our magnetic field B at point A. Okay, so let's say we want to find the magnetic field at this point A. Okay. To do this, we're going to set up an Amperian loop like we normally would. I'm going to be using Ampere's law, so I'm going to set up an Amperian loop here that has a radius equal to the distance from our symmetry axis here of A. Okay. Right, so R gives us our radius and our distance to A from our symmetry axis. Let me also write down our Ampere's law here. So we have again B dot dl equals mu naught, and what do we have? I enclosed, and I enclosed, let's remember, can now be, I should write it like this, can now be our conduction current and or our displacement current enclosed. Okay, so let's remember though that if we have a setup like this where we have just one induction current and we're dealing with a parallel plate capacitor, well, our ID has to be equal to our IC, because basically we need ID over the full, like if we consider all the displacement current going across here, if we think of it sort of like a real current flowing across this parallel plate capacitor, then we need all of ID here, if we take all of it, to add up to what IC is, right? Because we know we have IC going through. We have IC coming in, we have IC going out, so IC has to get across here. And that means that if we took all of the displacement current here, we would have ID equals IC. Okay, we'll make use of that in a second. Now this is only true if you have a setup like this. Let's say we had another wire running through here or something, then you had a loop which enclosed both of them. It wouldn't necessarily remain true that you had to have ID equal to IC. But for one wire bringing current in and current out of a capacitor, ID has to be equal to IC. Okay. So now what we're trying to do is we're trying to solve for basically B in this equation here. We know that if we're doing, well, maybe I'll draw the open surface here. So we have our Amperian loop, and it bounds this open surface that I've drawn here in red, this disk, right? So now we know the integral on the left-hand side, which is the integral around the loop here, is actually very simple to do, right? Because our b doesn't change because of the symmetry of the problem, so we can factor b out of the integral. The dot product isn't necessary because b is everywhere parallel to dl. And so we end up with, well, I'll just write it out here. We end up with b 2 pi r, right? And this is because when we are here, I'll do it in 2 steps in case anybody's not fully confident with it yet. So we end up with b, then the integral dl, and the integral of dl just ends up giving us 2 pi r because we're just integrating around a circle all the little elements of the circle. If you integrate around the full circle, you end up with the circumference of the circle, and so you end up with b 2 pi r. Okay, so that's the left-hand side. The right-hand side, we're going to end up with mu naught I enclosed. But what is I enclosed, right? So we're enclosing some current here. Now we're not enclosing any IC. We're not enclosing any of the sort of traditional current that we would think of, our conduction current, but we are enclosing some of this new displacement current, right? Now how much displacement current are we enclosing? Well, if let's say this is capital R. Okay, and this, let's remember, is lowercase r. I've scribbled over it here, but it's actually lowercase r. So if our lowercase r was equal to capital R, well, then we'd be enclosing all of ID, right? But now we're only enclosing some fraction of ID because we're only enclosing some small portion of the surface area of the space between our capacitor plates, right? So what we're really enclosing, we can write I enclosed is equal to, well, it's equal to ID, but not all of ID, some fraction. What fraction is that? Well, it's going to be the surface area of our disk over the full surface area of the capacitor plate, right? If little r equaled big R, well, then this would just be equal to 1, and we'd be enclosing all of it, right? So this is actually the fraction of ID that we're enclosing. We can clean this up. These pi's go away. This is equal to ID r squared over capital R squared. Okay? And so if we make our usual sort of assumptions that this electric field is uniform and so forth, we can sort of keep going along with this and expect to find an answer that makes sense, right? And so let's kind of put this together because we're now going to have this. This is our I enclosed, so we can plug that back into there. If we do that, we're going to end up with a b 2 pi r is equal to mu naught ID r squared over r squared, and we're trying to solve for b, right? So if we clean all this up, we can sort of factor all this stuff out, and we end up with a b equal to we're going to have a cancellation of r's here, so we're going to end up with a mu naught over 2 pi. We're going to have an r over r squared and an ID, right? And let's remember that for this setup, our ID is actually equal to IC, right? So we can rewrite this one more time. Let's rewrite this one more time in terms of IC because it's nice to have it in terms of this easy to measure current. Like we could easily put a galvanometer or an ammeter in this conductor, measure what that current is, and then we could right away tell what the magnitude of our magnetic field was at that point. And it would be more difficult to measure ID, right? ID would be more complicated. We'd have to measure the electric flux going through here, much more complicated. So if we write this in terms of IC, which we can just replace ID with because we know they're equal, we end up with this expression here. Oops, I was going to square that, but that's not squared. Okay, and that is the magnitude of the magnetic field at the point A. Okay? Okay, so like I said, there is more to this section, but I'm going to leave this video here. So we're going to stop here on displacement current. In the next video, I'm going to do a quick sort of look at Maxwell's equations, which is the last part of 29.7, and that will be the end of this chapter. Okay? All right, so I'll leave you guys here, and I'll see you in the next one.